So now in this video, we're going to use a dual supply op amp as an inverting comparator. And so here is the basic circuitry. We are going to use the JRC4558D op amp. There's actually two of them on the integrated circuit. So one of them we're going to use for the inverting comparator circuit, and the other one we're going to use to make our ground, our 0-volt reference point. We're going to use 8 volts, and using that half of the op amp, one of the two op amps I should say, we're going to take that 8 volts and split it into positive 4, negative 4, and then ground, the 0-volt reference point. So in any case, we are going to set 0 volts, in this case, to the non-inverting input, because we're going to use two equal value resistors between positive 4 and negative 4 volts right there. And so I found with this particular op amp, I don't know how many op amps have this problem. I tried out 3 of them, and then I tried moving it on the breadboard, but all of them, they don't work properly if we get the non-inverting input 2 volts away from the negative supply, which would be negative 2 volts in this case. So I got to stay above that, and actually probably negative 1.5 volts. But in case, we got to stay above that. 0 volts is way above that. We should have no problems with this circuit. So now notice on the schematic that the non-inverting input is above the inverting input. When we get to the actual integrated circuit, the inverting input will be above the non-inverting input. So we have to make sure that we wire them up properly, that we get our fixed voltage divider to the non-inverting input. Now the inverting input, we're going to use a 10 kilo ohm trim pot where we can get anywhere from positive 4 volts to negative 4 volts. Now, since it's an inverting input, that means that when the input here, the inverting input, is positive 4 volts, the output's going to connect as close as it can to negative 4 volts right there. And I'm going to use a blue LED to light up in that case right there. So we are going to use a 1 kilo ohm resistor. We can go lower, probably to about 150 ohms or anything higher than that. And the higher resistance, just the less bright it gets. We're only dealing with probably about 2 volts going across the resistor either way, because the LEDs drop 2 or 3 volts. 2 for red, 3 for blue. So now, let's go to the other extreme here with the trim pot. We get closer to negative 4 volts. Actually, we get about halfway. It flips. So once we get more negative here, then the output gets a positive voltage there. So not quite up to 4 volts, but pretty close. And so then we have the red LED here. You can see the current path. The red LED will light up if you want to color code them. So for this circuit, that's really about everything there is to it. Here is the pin layout from this kit. As you can see here, we got one op amp on one side, the other on the other side. We have to power it. So on the data sheet, it actually says plus VCC and then minus VCC instead of ground right there. This does not work very well as a single supply. For the most part, some single supply circuits though will work, such as we're going to make a virtual ground right there out of a single. But in any case, you can see the non-inverting is below the inverting, and then the output is on top right there. So on the schematic, the non-inverting was above the inverting, but the physical component, you got to make sure that you have them correct. The non-inverting is always below the inverting for this physical component. And here we are on the breadboard. There's the negative supply. We have a 10 kilo ohm resistor coming to another 10 kilo ohm resistor, which goes to the negative supply. So positive, negative, so that gives us half the supply voltage. We have the trim pot here. It's more negative right there. The red LED is lit. I turn it more towards positive up there, and the blue LED lights up. So we got the fixed resistance at the non-inverting input, the adjustable resistance to the inverting input. That's what makes it an inverting comparator. The blue LED, as you can see, we got the short lead to the output top pin. Long lead, the anode is up one spot, and then the red LED, long lead anode to the output, short lead cathode up one spot. That up one spot, there you can see that they connect to the top pin there, the output, and their top pins connect to that resistor, which comes to the other op amp. on here. So that's our virtual ground. That gives us half of the 8 volts that we have there. We can pull back, and that's just a voltage follower circuit right there, set to halfway. But in any case, we got 0 volts there. The oscilloscope is not connected to anything right now. It has alligator clips at the end. They are clipped to jumpers. And so what we can do is go to that virtual ground. We'll zoom in a little bit to see a little easier. And we're at the virtual ground. I covered that in the last video. Now we're going to take the red one right here and go to the output. So that is the top pin right up there. And there you can see that we're just shy of 4 volts positive in relationship to 0 volts. I will turn the trim pot up to get a high input and get a low output right there. And it goes to ground. So if you saw the last video, we had a non-inverting comparator on here, and if I went down too low, it flipped back. So it flipped back to making a low output. Actually, yeah, we got the high output, and in that video, turning it low gave a low output, but you go low enough, all of a sudden it flipped high for some reason. That's just this particular op amp. So high input for the inverting, low output, and a low input for the inverting comparator. We have a high output. That is why it is inverting. So now you don't have to use an op amp to get your split supply here, which is a dual supply. I also have this integrated circuit, which I showed a couple of videos ago. We can just go to that, and we got the same thing, red LED right there. And also some supplies just come with the capability of making a dual right there. So low input, high output, and then higher input than halfway, because that's what we set, halfway, and we have a low output right there. Now this is a dual supply. I noticed that dual supplies don't get all the way to the rail voltages. So in relationship to ground, we got +4 and -4, and so that's 4 squares up to the very edge, and then 4 squares down to the very edge in relationship to ground. You can see we go to the positive supply, now we got more voltage, and to the negative we also got more voltage. So a lot of times it's the load that is pulling it away, but in this case, if we remove the LEDs, the output stays the same. So I'll plug that into the output. There's no LEDs, so there's no current flowing in or out of the outputs. And you can see they still don't make it to the rail. They make it slightly closer, rail to rail, but not all the way to rail to rail. If they did go all the way from one rail to the other rail, it would be called a rail to rail output right there. So in any case, that's really about it. Hope that all made sense. Hope you enjoyed. Make sure you check out one of the other videos that I post to the screen. Click like, subscribe, the bell, all that. Donate to Patreon if you can. That helps out the most. But just watch as many videos as you can. Helps out a ton. So thanks to everybody that does that. I will see you in the next video.